When atmospheric carbon dioxide reacts with oceanic water, carbonic acid is formed. Carbonic acid has a relatively high dissociation constant in seawater, which causes the compound to split and dissociate into a bicarbonate ion and a free hydrogen ion. Acidity of a solution is the measure of pH, which is a measure of free hydrogen ions. The more hydrogen ions in a solution, the more acidic the solution is. Like carbonic acid, bicarbonate also dissociates into another free hydrogen ion and carbonate. The process of acidification therefore contributes 2 hydrogen ions for every 1 molecule of carbon dioxide. Atmospheric carbon dioxide concentration has reached an average of more than 400 parts per million, which is nearly double the concentration of pre-industrial times. Considering the global ocean is the world's largest carbon sink and gas concentrations work along a gradient, the ocean will continue to absorb more and more carbon dioxide, working towards an equilibrium with the higher concentrated atmosphere, furthering ocean acidification. So why do we care about acidification? Economically and ecologically important organisms like shellfish and coral create their shells and skeletons with calcium carbonate, which dissolves under acidic conditions, leaving carbonate-based organisms like shellfish and coral, unprotected and stressed. Coral operate comfortably in pH between 8.4 and 8.1. However, since 1750, pH has decreased from 8.2 to 8.14, roughly a 30% increase in acidity. Most corals are made of a polyform of calcium carbonate called aragonite. This form is less stable than the other form, calcite, and is therefore more susceptible to acidification. Although calcite is stronger, it is rarely formed and sometimes only used to fill skeletal gaps of aragonite. Hard-bodied corals such as Acropora and Montastria, under the order Scleractinian, are primarily made of aragonite and are expected to decline with decreasing oceanic pH. Experimental results show that softer-bodied Gorgonian corals, also known as sea fans under the order Alcyonaceae, that form their skeleton out of magnesium and calcite are expected to diversify and better deal with this declining pH. Here you can see the stony-based coral community that is characteristic of the southern Caribbean compared to a protected region of the Florida Keys in which Gorgonian corals are much more abundant. Another negative effect of climate change on coral is how commensal dinoflagellates, called zooanthellae, react to changing pH and warming water. Zooanthellae live inside coral skeletons and receive protection from outside forces, while contributing a large portion of the coral's energy intake, about 95%. When zooanthellae are put under warmer water temperatures and acidifying conditions that are both characteristic of higher carbon dioxide concentrations, they become stressed and leave the coral in a process known as bleaching. Here's an example of bleached coral. In 2005, the U.S. lost half of its Caribbean coral in 1 year due to a massive bleaching event. Coral reefs are primarily based around coastal boundaries and are therefore subject to river flow that empties into the ocean. River flow is expected to increase with changing hydrological patterns with more evaporation and precipitation in the form of rain. Increased river flow leads to an increase in turbidity and eventually more headland sediment being deposited on coastal oceanic margins in a process known as sedimentation. Deposition of this material on reefs inhibits photosynthesis of zooanthellae and some others coral, eventually leading to an increase of macroalgae and possible death of the reef. It is evident that climate change is currently happening and expected to become even more accelerated in the future. As mentioned before, coral are slowly starting to shift from less stable forms of calcium carbonate to softer-bodied calcite magnesium types like Gorgonian due to rising acidity levels. With large-scale bleaching events occurring more often than ever before, our ocean is likely to see a huge loss in biodiversity in the coming decades. The only way to lessen the effects on coral reefs is to better manage anthropogenic carbon dioxide emissions and clean up our shores in the hope that we are acting soon enough.